Alright, so we're going to wrap up this unit with talking about vector equation of lines. So we often have lines traveling not in a two-dimensional space but in three dimensions, and we're going to use vectors to define those lines. So the general idea of what we're doing, and then we'll do an example. But what we're trying to do is we have some line in space that we're going to symbolize with a vector. So we have some vector in space that we want to be able to basically find any point on that vector. And so we have to have a known point. We have to know something that actually lies on that line. Otherwise, we don't have it grounded. Because remember, we can move vectors around wherever we want as long as we keep the direction and the magnitude the same. So we need a known point which fixes it in space. And we're going to need a unit vector that's in the same direction as our vector. Well, we can do that because we just take the magnitude of the vector and divide it by everything by that magnitude. And so that'll give us a unit vector. So that's easy. And then what we're going to do is we take a point that we want. So we're going to take a general point that's a known distance from D. So this distance D is what we look at. So we take that XYZ point that's a distance D from our known point. And D is going to remain a variable so that when we want something 12 feet away, we plug in 12, or 0.3 inches, we put in 0.3. So that's going to be something that is our variable that allows us to get any point that we want. So now what we do is we add our vectors head to tail. So we define a position vector, vector P, to our known point, and then we scale that unit vector by our distance V, and that gets us to any point that we want. So if we want something, like I said, 15 feet away from the known point along the vector, we just add those two vectors. We take the unit vector, scale it by 15, and then add the two vectors to our position vector. So that's what we're doing, and we get this resultant vector, which is a position vector. So it's the resultant of adding the first position vector and our scaled unit vector. So that's what we're doing. Let's look at an example of how that works. So how do we do it? Well, we want to find the vector equation of a line. Let me speed this up a little. From these 2 points. So we have two given points, and first thing I need to do is to calculate a displacement vector between those 2 points. So here's my 2 points. I'm just going to call them A and B in space. And I'm looking from A to B, and I calculate that displacement vector. I just subtract my quantities. So that becomes my vector. And I want to find anything along that line, so along that vector. So what we're going to do is get a unit vector. So I divide by the magnitude. And that becomes, if I calculate the magnitude, is 21. So I do everything divided by 21. That is going to be a unit vector in the same direction as AB. So I know my origin is floating around there somewhere. And again, it's hard to draw these in three-dimensional space, so it's just kind of our best guess at it. And I define a position vector P. And it's easy because it's just the components of A, the order triple for A. And then I pick a general point XYZ along my vector. And the resultant vector is going to be give me that any point that I want along that vector. So to get to that, I have to add some distance times my vector U that we figured out. So I'm just scaling that unit vector and adding it to the starting point of A, and that gives me any point along around there. So I can imagine stretching or shrinking that yellow vector to get to anywhere I want along the green vector. What that looks like algebraically is this. So if I add them up, I just add the components. Alright, so I take my values. There's vector P, there's D times vector U, and then combine your I, J, and K values, and you get this expression. So that is the equation of the line for that vector in space. We see we have a variable D in there that allows us to get to anything that we want as we go through this. So how might this look? Let's say that we have our vector expression. So there's our line, the equation of that line. And we want to know where it intersects a given plane. So we have a plane, and we want to know where does it intersect that plane. What's the point? What's the order triple where it works, where it satisfies 40 equals 2x minus 3y plus z. So what we're going to do is we're going to use our values here. We're going to use both pieces of information to figure out that point of intersection. Alright, so we know that if we were to plug through this, X, Y, and Z are going to be our component parts that are attached to I, J, and K. So what we're going to do is we're going to set that, we're going to plug those in for x, y, and z. So 40 has to equal 2 times my x value minus 3 times my y value plus just my z value because it's 1z. Well, now again it's just going to be algebra as we sort through it. So I distribute and I simplify everything and I'm solving for d, so I get some fraction with d. I add everything up and I get 40 equals 25 plus 3/21 d, and d equals 105. So that's d, but that's not my answer. To figure out what I actually have as a point, I need to plug in 105 for d into my equation for r. So r equals 26i plus 38j plus 102k if you put in d is 105. So my point of intersection is 26, 38, 102.